Dr. Abhishek Majumder is an assistant professor at Reading University at UK, but I know him from 2015 when I started my PhD at University of Copenhagen. He was starting a postdoc there, and after that he moved to Sweden, then Singapore, and then he came to UK and become assistant professor in statistics. Dr. Majumder, please go ahead.
Thank you, Amir, for the introduction and for inviting me to give a talk in this Future Algorithm 2025. So this talk actually, I'm working on this field for quite some time with people like Professor Karsten Youth from University of Copenhagen and Dr. Daniel Capelletti. So this is regarding a thing called reaction networks, or more precisely, stochastic version of reaction network, which I will define in the first few slides of this talk. And then I'll come to certain important problem regarding long-time behavior of stochastic reaction networks. And then I'll come to the point where what this non-regular means and what I want to do about it. So, okay, let's begin with it. So what is like stochastic reaction network? And these are some structure of this talk. So usually, a reaction networks is basically a dynamics of few species that interact with each other in forms that are similar to chemical reaction. So it is a dynamical, we study the dynamics of the interacting species. So this is an example of how three different complex, each of the, A plus B is one complex, 2A is another complex, and 3C, that is another complex. They interact with each other. So A plus B goes to 2A by some chemical reaction, and then 2A goes to A plus B, that is via some chemical reactions, and so on and so forth. So if we define the species would be the basic molecules that composes these complexes, and they are A, B, and C. That are the species. And since we are here modeling the reaction mechanism based on the species molecule counts, so we take this species to take values from the space of integer n to the power cardinality of the species space. So since we are just modeling the count of the species that are interacting via these reactions. And then complexes are this A plus B, 2A, 3C. And reactions are composed between two complex in the, each reaction is kind of a subset between C cross C. That basically means that for any two complex, there can be a possibility that there is a reaction between them. And the whole set of reactions is denoted by this R, script R. And most important part is this thing, this is called the rates, which basically determines the speed of the reactions. And that are functions that takes values from this species count space, which is some sub n to the power mod s to something that is non-negative. So this is basically how usually, these are the four things are stuff that defines the structure of reaction network. But then I'll explain what stochastic reaction network means. So in stochastic reaction network, we model the number of number of molecules taking part in these reactions, and we see their dynamics over time. And also each of these reaction takes place in the instances of Poisson processes. And if I explain the whole the previous dynamics in terms of mathematical terms, so in deterministic reaction network, we model the concentration of each species. In stochastic models, we model the counts of each species. And here, xt denotes the species counts of all the species taking part in the reaction at time t, and x naught is basically at time 0 the species vector. And yi of this, it's basically, so this is the value of the aggregated reaction rates corresponding to this y to y prime, that reaction. And yi, I mean I from for each of the reaction taking places, yi are sequence of independent unit rate Poisson processes, and y prime minus y are the, basically for every reaction, it is the change or change in the species counts, and that is basically elements of stoichiometric subspace. I mean, I know this may look very um, complicated, but it will be, this structure will be very simple when I'm explaining the example that we had seen in the last slide. So another thing is that there are various types of reaction rates that people consider, and most usual type is actually called the mass action kinetics, where these reaction rates are defined in this form. So it is a kappa y to y prime. This is a constant, and x factorial divided by x minus y factorial. It's basically for at when the species counts are x, then this is the aggregated rate for the corresponding y to y prime reaction given by this mass action kinetics. So if I see that under mass action kinetics, how the last reaction that looks like, so we start with the initial counts of species taking places in these four reactions. You have A naught, B naught, C naught are the initial counts, and AT, BT, CT are the species counts at time t. And the first reactions is basically the number of, so y1, this quantity, this basically means the number of times up to time t, the first reaction, which is A plus B to 2A, that reaction is taking place. And in this, when the reaction is taking place, then the change in the species space happens by this particular factor, because A plus B going to 2A, that basically means that A gets increased by 1, and that is here plus 1. B decreased to 0, which is minus 1, and there is no C that is taking part in this reaction, so C is 0. Similarly, second reactions, so y, this counts the total number of reactions of type 2 that is taking place in time t, up to time t, and this is the reaction gradient, and similarly this and this. So this is the way you can actually study the dynamics of species counts over time for any arbitrary reactions, and that is modeled by the stochastic reaction network. So this is something that is established, and there are certain connection between the stochastic reaction network and deterministic reaction networks that are in the literature as well. But here I'm interested in studying the long time behavior of these stochastic models that is prescribed by this stochastic reaction network. So uh, we define a few terms, and one thing is called equilibrium distribution, or it is also called the stationary distribution. So it is defined as that if the initial distribution of the species counts is given by a particular law or distributions, for every time it will be that distribution, and that distribution, I mean, if that exists, then we call that mu is the equilibrium distribution for the reaction stochastic reaction network. And then there are certain interesting results for this kind of structure of this limiting distribution or equilibrium distribution of stochastic models. So a, a reaction network contains a complex balanced equilibrium, and that is a value C such in a deterministic mass action system, such that this condition holds for all y belongs to C. So this is a particular property, this complex balanced equilibrium. If a reaction network contains a complex balanced equilibrium, then it is shown by Anderson Capelletti cards in 2016 that the corresponding stochastic models will have a equilibrium distribution that is given as a product form of Poisson type of mass function. That basically means that, okay, so there is m gamma c is the standardized sorry, normalizing factor, and this is actually pi gamma x is basically is proportional to the product of ci to the power xi factorial, where c1 c2 c think these CIs are coming from this complex balanced equilibrium, which is something that we assume that corresponding reaction network holds. So that is a good result, and that defines a large class of, I mean, equilibrium distributions for large class of reaction network. So there are also some interesting results that if a reaction network contains a complex balanced equilibrium, then it can be shown that this reaction network can be weakly reversible. So I don't define this term called weakly reversible. Weakly reversible means that when there is a reaction from one species y to y prime, then there exists a sequence of reactions from y prime that also goes to y. So that property is called the weakly reversible. I mean, when you have for any two complex y and y prime, if y goes to y prime, reaction is contained in the reaction space, then there is a sequence of reactions from y prime that leads to y. And if that property holds for all complexes, then the reaction network is considered to be weakly reversible. So there are some there are some results that shows that complex balance equilibrium implies weakly reversible, and then weakly reversibility plus another property called that is called deficiency equal to zero, which I'm not defining, that also implies complex balance equilibrium, that network contains a complex balance equilibrium. So in a very overall sense, if I want to generalize, the complex balance equilibrium is kind of, in a way, it is if the network is, or the reaction network is weakly reversible, then we can say it has a complex balance equilibrium in a very overall, very loose sense. So if I have this very simple reaction, so 0 goes to x1 and x1 goes to 0, and then 0 goes to x2, x2 goes to 0, then so this is a very nice weakly reversible reaction, and it is also known that, I mean, it is also complex balanced equilibrium. It has a complex balance equilibrium, and then using the last result, we can show that this the species counts x1 and x2 at infinity, or the equilibrium distribution can be expressed as a product of Poisson beta by lambda 2 and Poisson beta by lambda 4. And there is beta by lambda 2 and beta by lambda 4 are basically the complex balanced equilibrium quantity. So, but then there is another reaction, and this is a particular case that the reaction is no longer weakly reversible. And actually, I mean, I'm not going into too much detail, but it is expressed in this particular paper 2013, that this is no longer an ergodic reaction, which basically means that it does not have a um, I mean, long time. I mean, it does not. I mean, at t going to infinity, the x1 infinity and x2 infinity, that does not converge to a particular distribution. And the way they had shown is that they showed that probability of x1t greater than m for any finite m, as t going to infinity, this probability will be greater than half, which basically means, and this is true for all m, that basically means that in the plus infinity, you will have certain mass in at t equal to infinity, and at minus infinity, you will have certain mass. So that is which basically shows that there exists no limiting distribution, time asymptotic distribution for the species for that taking parts in these reactions. So the question that comes from this whole space is that for the complex balance equilibrium, we know that there exists a limiting distribution, as a time asymptotic distribution that is considered to be also the equilibrium distribution. So what happens for uh, time asymptotic distribution for reaction networks that are not weakly reversible? So this was the starting point of the research that we had conducted. So this is a particular type of example where you can see that there are three different species, G1, G2, and P, and this is actually an example of gene regulatory networks without feedback, where G1 is unactivated gene and G2 is the activated gene. So G1 goes to G2 with rate lambda 1 and G2 goes to G1 with rate lambda 2. And then the protein gets synthesized in the presence of the activated gene. So it basically says that G2 goes to P plus G2. And then in presence of inactivated gene or deactivated gene, we have the protein gets also absorbed, or yeah, so P goes to 0. So now you can think of this whole reaction under mass action kinetics, that G1 and G2 are actually something that is going on in the environment. And the reason I'm calling this as environment, because in these two reaction where protein gets synthesized and protein gets absorbed, here G1 and G2 counts are not getting perturbed. So here G2 remains same, here G1 remains same. The total species counts of G1 and G2 does not get affected when these two reactions are taking places. And also you can see that you can write this reaction under mass action kinetics, these two reactions, as 0 goes to P and P goes to 0, where your reaction rates can be written as alpha multiplied with the total counts of G2 at particular time point, and this P goes to 0 when you can write these reaction rates, beta will be multiplied with G1 at that particular time point. These reactions can be seen as a monomolecular reaction for species where the reaction rates are driven by certain types of stochastic environment. And this is another type of example. This is not coming from some real valued example. Here S1 and S2 that define some environment, and then T gets synthesized and T gets absorbed in the system that is dependent on this stochastic environment that is given by S1 and S2. And so if I generalize this kind of reaction, and this is something we call that as a host parasite reaction network, uh, we can actually write two types of reaction network. One is called host reaction network and another is called the parasite reaction network. So if I give a bit of context in this particular reaction, G1 and G2, they are actually driving the environment, which is called, we call G1, G2 to be host, and P, the proteins are called the parasite, because the rate of synthesis of P depends on G2 at time T. Similarly, I mean, without G1 and G2 present in the system, this reaction does not, I mean, the dynamics of this reaction cannot be studied. So P is considered to be as parasite. Similarly, here S1 and S2 are host and T is parasite. So host, we consider that there is a host reaction network, and then there is a reactions networks of the parasite, and the way these parasitic reactions taking place under mass action kinetics is that the production of parasites happens when 0 goes to P, I mean H naught I goes to H naught I plus Pi. Similarly, Pi goes to Pj in presence of Hij, and similarly Pi goes to 0 in presence of Hi0, and H naught I, Hij, and Hi0 are all complexes that are coming from these host reaction networks. And under mass action kinetics, the property that comes from this structure of these host parasitic reactions that coming, I mean, that is infused in this causal type of structure, that all species, host species at time t, their counts is independent with protein species or the parasite species at time s, condition on the whole history of the host dynamics before time point s, for all s less than t. So if, I mean, this is actually the way we create this host parasite reaction that implies this. So if that happens, then we can actually prescribe the joint distribution of this host species and the parasite species, and I mean joint equilibrium distribution of the host species and parasite species. And interestingly, all these reaction, if you see, these are all non-weakly reversible reactions, because you can see G1 goes to G2 and G2 goes to G1, that are taking places, but G2 goes to P plus G2, then there is no reaction from P plus G2 that goes to G2. So that makes this whole reaction R1 star to be non-weakly reversible. So these are actually, we are trying to give certain structure of non-weakly reversible reactions, and we can actually get the equilibrium distribution of this species, host species and the parasite species together jointly via that contains this structure. And when I'm trying to understand the structure of that reaction, an important quantity that takes place, and that is called as stochastic recurrence equation. And if I take a little bit detour to explain what this thing is, so we all know that for any real a and b, when mod b is strictly less than 1, this infinite geometric series converges to this particular quantity. We know that. But what happens when a and b are replaced by random variables, where a1 b1, a2 b2, a3 b3 are coming from this joint distribution of a and b, and then what this particular random variable x, I mean, what the distribution of x will be equal to, and that is the question that I'm starting to ponder. And if I write this in this form, you can see that these all the terms that are coming from the second term onward, b1 is a common term, and x is defined by this random variable that is defined by this particular sum. So you can see that this whole sum is identically distributed as, if I take the b1 common, then the residual part in the first bracket would be identically distributed as this whole thing, that is the x. So if this random variable exists, then this particular sum of this random variable, I mean sum of this product of these random variables satisfies this kind of recursion equation, which is x is identically distributed as a1 plus b1 multiplied x, where x is independent of a1 and b1. And these are the two conditions in one dimension that prescribes that uniqueness, existence and uniqueness of a random variable x that satisfies this recursion equation. So x is defined by this solution of the stochastic recurrence equation if it satisfies this. And in one dimension, the existence and uniqueness condition, in a very loosely speaking manner, are this thing. And it is also used in a lot of other direction in finance, in Gart's process, in time series, and also exponential functional Levy process. So it is extremely well used in different domains. So now we'll explain. So I'll remove this particular thing. Now we'll explain how this host parasite reactions equilibrium distribution looks like. So under there are three conditions, and this is a result that we had published in a paper in 2021. It suggests that if HT is marginally ergodic with host species are marginally ergodic with stationary distribution pi gamma j, and then all the properly produced parasite species have a path of degradation, and expected production rate of each parasites under this stationary distribution of the host is finite. If three conditions hold, then we know that this is jointly ergodic, and then the joint distributions can be expressed, I mean joint equilibrium distribution of host and parasites can be expressed as mixture of Poisson distribution. And mixture of Poisson, that is kind of expected, but here you can see that h equal to j, that limit, I mean that host species limit will be the stationary distribution that is assumed here. I mean it is the first assumption. So pi gamma j, that is the actually the limiting distribution for host species at species count j. But then the mixture of Poisson contains this measure mu j. And this is where the idea of that stochastic recurrence equation that I just explained that will come in handy. So what is this mu j? So I did not explain it thoroughly, but mu j can be expressed as a distribution of the fixed point of a stochastic recurrence equation of this form, where A and B are are defined. I mean, are two random variables that are defined by the host species dynamics into two different time points. So that are in a um, very vaguely the results that we had done in the paper 2021, but there are certain limitation of these results. So the way we had expressed these reaction stochastic reaction networks, the all the sojourn times are non-exponential. But in a general manner, in arbitrary reaction mechanism, we should expect to have the sojourn times to be non-exponentially distributed. Uh, so that is one of the limitations. And then also the sojourn time distributions uh, I mean, in our model by this continuous time Markov chain based model, it is not, it does not account this possibility that the sojourn time distribution of the host species can depend on the next future state as well as the current state. So that goes against the Markovian property. So how to accommodate this? So this is basically how one can accommodate, instead of Markovian host species dynamics, how to accommodate the semi-Markovian host species dynamics. And in that case, what would be the limiting limiting distribution of the host species and the parasite species? So I'm not going into the details of this semi-Markovian structure. It is actually, I mean, you can see it in Wikipedia, and it's kind of little messy here how this host species dynamics looks like under semi-Markovian structure, but I can show you the end result. So if certain under certain good conditions hold, then actually this under semi-Markovian host species dynamics also, you can have this parasite dynamics of this parasites at t going to infinity and dynamics of the host at t going to infinity. It can be written together jointly to, it can be written as a mixture of Poisson where ht equal to j that go has a limit this pi gamma j, which is some sort of assumption that we had. But jointly you have this thing that is a multiplicative part to this, where this mixture of Poisson, it is again coming here, and you can explicitly write down this mu j. And here you can see that how this mu j is related with that stochastic recurrence equation that I explained. So this mu j can be expressed in these two type. One is the red thing and one is the black. And the black part is satisfies this stochastic recurrence equation where aj star and bj star are certain functional of the host species up to two different time point tau naught to tau 1j, which is the first hitting time to state j to the second hitting time to state j by the host species. And similarly, this is also another functional of the host species dynamics from the tau naught to tau 1j. And aj star and bj star looks like this. And this blue, red part contains only random quantity that is called tj, which is the size bias transform of the sojourn time, aggregated sojourn times at jth time point. And that has a distribution which is in the last slide that I did not explain properly, but it looks like that, and it is coming from the host species dynamics. So you have a structure I mean, structure of the limiting distribution that is explained like this. But the point is that, yes, I know Amir shows up. I'm finishing. So there is a way to simulate from this. Sorry for this. Uh, okay, so yeah, I don't think I have that part here, but there is a way to simulate from this limiting distribution, and that is via certain sampling techniques. and that use this particular structure that we have here. Okay, I'll finish here and I'll take any questions that you may have. Thank you.
Okay. Thank you, Dr. Majumdar, for the talk. If there is any question from the audience, we can have one too. Any questions? If not, I may ask something quick. So on the
Yeah.
slide 10, you had an example from commotion, others that the probability at the infinities still have a positive mass. Is it also an example of heavy tail distribution of the previous speaker?
Uh, um, we- so uh,
But it's
the
not alpha
thing,
is stable because it's not converging to zero. It's very
no,
positive.
the
But
issue, yeah, but the issue is that when we are, yes, so heavy tail is a possibility under certain cases, but not for in general for all cases. The reason is that here we have this sojourn times dynamics plays a very important role here. Sojourn time dynamics plays a very important role. So this exponential sojourn times that leads to this product of this poison type limit distribution, and the poison has tails that is lighter than way lighter than the normal distributions, where alpha equal to 2 if you had seen
mm,
last week's talk.
right,
So alpha smaller than 2 is considered to be heavy tail.
I see.
So
I
yeah,
have to
so
check the
I
definitions.
yeah, no,
Mm,
I don't think for usual cases we have heavy tails coming from the stochastic reaction method, but certain cases like branching type of process, there is a possibility of having that, but very critical and certain cases. But in general, it is not easy to. So I saw another question. Have you
yes.
considered or tested your stochastic models on real biological datasets? No. And the reason is that because it is kind of a theoretical question and we want to study the existence and uniqueness of the limiting time asymptotic distribution for general class of reaction network, and we only considered here the non weakly reversible cases, few cases. So yeah, I have not done any, or I have not considered any real life but one thing is that this gene regulatory network, it is kind of a real life examples, and you can see gene regulatory networks under non-feedback assumption is something that you can see in many examples and in synthetic biology. So yeah, so there are applications of this result, definitely.